Today, we're talking about pyramids and a little bit about how they're different from prisms. So you might be able to take a look and notice the physical differences. And one part, I guess, if we're talking about prisms, we know that the lateral faces are represented by rectangles, and that the base of the prism defines what kind of prism it is and what formula we use in order to find the volume and surface area. Pyramids are a little different, as you can tell. First thing we're going to do is take a look at a few of the pyramids. You'll notice we have a tetrahedron, we have a square pyramid, and we have a pentagonal pyramid. Now, if you notice, all of them have triangular faces that meet at a common point. Because they have triangular faces that meet at a common point, we call the solids pyramids, and the triangular faces are called lateral faces. So before, where we had the lateral faces of a prism, and we noted that they were rectangles, now we're taking a look at our pyramids, and we notice that the lateral faces are triangles. So back to our pyramids. Again, we have a triangular pyramid, a square pyramid, and a pentagonal pyramid. Again, just like with the prisms, we use the bases to define what kind of pyramid it is. Now, we're going to get into a little vocabulary when we're referring to our pyramid. First thing we need to talk about is the common point at which the lateral faces meet. That is known as the vertex. The perpendicular from the vertex to the base of the pyramid is known as the height. And you'll notice I know it's a perpendicular because I've got the little box there that tells me I've made a 90-degree angle. Then, so if you're looking at it from the side, we have this distance as the height. Then what you're going to do is see the common edge between two adjacent lateral faces. So the point where two lateral faces connect, that is known as the lateral edge or the slant edge. And let's see, we've got the height, and of course the lateral face, as we've shown before, is the part of the triangle that folds up to make the pyramid. Then, of course, at the bottom, or the base, if you will, which makes it very self-explanatory, is the base of a pyramid. All right, so those are the different values, the different terms that we will be using when discussing pyramids. Now, if the perpendicular meets at the center of the base, then the pyramid is a right pyramid. If the base of the right pyramid is a regular polygon, then the pyramid is a regular pyramid. So I guess the idea of this pyramid was to make it a right hexagonal pyramid. Next thing we're going to do is focus on the nets. Now the net of a pyramid is actually kind of fun because it's pretty much based on the center value or the base of a pyramid, and then you just have different types of triangles that fan out from that base. So now again, if you look at it in terms of a net, you could see where the base over here is a triangle. That makes it a triangular pyramid or a tetrahedron. Then we have the square pyramid over here in the middle, and then over on the right we have a pentagonal pyramid. Again, the base defines what type of pyramid it is, and they all meet at a common point at the vertex. So if we're trying to find the total surface area of a pyramid, we can see that it's going to be the base area plus the base area plus the area of all the lateral faces. So a lot of triangles are being used, which means we're going to be using quite a bit of the Pythagorean theorem. Here's an example, dealing with surface area. Each lateral face of a triangular pyramid is an equilateral triangle of side 2 centimeters. Find the surface area of the pyramid. So what I'm going to do first is go ahead and take a look at the net. And what I want to do eventually is find the surface area of the entire shape. But before I can do that, I know it's an equilateral triangle, so I know there's going to be 4, which means if I find 1, I can just take that value and multiply it by 4. So let's take one of the triangles, and we're going to bring it out over here. There we go. All right, and let's just label this V, A, and B. Why V? Well, you can see it's going to come up at the vertex point and meet up at the top. So we're going to go ahead and talk about it that way. All right, so I know each lateral face is an equilateral triangle of side 2 centimeters. So I know this is 2, this is 2, and I know the distance from A to B is 2. What I'm going to do is create a height and label that point M. I know then if I've created a perpendicular from the height, I've split A and B directly in half. So I know that AM and MB will both equal 1. Now what I can do is go ahead and take that half of a triangle. So again, here's B, here's M, the point I just created. Here's A. Hey, BMA. All right. And I know that this is 1, this is 2, and the height is going to be my unknown. So I'm going to set this up using the Pythagorean theorem as 2 squared is going to equal 1 squared plus the distance VM squared, which is going to be our height. So I have 4 equals 1 plus h squared. And I subtract 1 from 4, so I get 3 equals h squared. So then h equals the square root of 3. All right, why did I need that information? Because in order to find the area of a triangle, I need to take 1/2 times the base times the height. I did not have the height before. Now I do. And that'll give me the area of one of the triangles. So then I have area equals 1/2 times 2. What's that? It's 1 times the square root of 3. Which means then the area is going to equal the square root of 3 square centimeters. So the area of one triangle is the square root of 3. And I'm just leaving it as the square root of 3 right now. I know you're tempted to convert that irrational number to something else and use the decimals, but wait until the end. So I have 1 square root of 3, which means all of these equal the square root of 3. So the surface area of the pyramid is going to be 4 times the square root of 3, or 4 root 3, which correct to 3 significant figures is going to be 6 and 93/100 square centimeters. So far, so good? I think so. Next, what we're going to do, ooh, look at this. VPQRS is a right rectangular pyramid with a height of 12 centimeters. And PQ equals 10 centimeters. QR equals 8 centimeters. Find the total surface area of the pyramid. All right, so there are a lot of different things we have to put together. First thing I'm going to do is construct perpendiculars VM and VT, which means I'm going to make this over here. It looks kind of funky, but it is cutting directly in half, and there's a right angle. And then I'm also going to cut this way. So we're going to use this as T and this as M. All right, so what I've done is constructed perpendiculars so that what I can do is find lengths in order to be able to solve my problem. Here's how it's going to work. All right, so I know that N to M is equal to T to Q. So I know that N to M is going to be 1/2 of P to Q. So that means that's going to be 1/2 of 10, which is going to get me 5 centimeters. So N to M equals 5 centimeters. Now if I look in the other direction, okay, so now that I have that, what I'm going to do is go ahead and find V to M. Because what I want to do ultimately is find the height of this triangle. Maybe instead of saying this, what I should do is draw the net. So if we're taking the net of this pyramid, and it keeps going that way off the screen, trust me on that. Here we go. All right, so what I need to do ultimately is find this height. And that height that I just drew in the green dotted lines represents this height. So I already found that N to M is 5 centimeters. So now I have a length of 5 and a length of 12, which means now I need to find that third length, again over here in green. That's going to get me the height of this triangle. So then what I'm going to do is go ahead and use the Pythagorean Theorem. I know that 12 squared plus 5 squared equals whatever that length VM will be. So VM squared, that's going to be my height over here. So then I have the square root of 12 squared plus 5 squared, which really is 144. So the square root of 144 plus 25, which is 169. That's going to get me 13. So now I know that this distance, the height of this side length, is 13. So if I want to find the area of this triangle, which by the way is also going to be the area of the triangle opposite since they both have the same side length, what I'm going to do, the area of triangle VQR, is I'm going to take, so triangle VQR, there's a lot of work here and I understand, but you can go ahead and pause at any time just to catch up with your thoughts and know a step at a time, see what's happening. All right, where was I? So I have 1/2 base times height, and the base we know is 8, and the height of the triangle we just found as 13. So the area of triangle VQR is 1/2 times 8, which is 4, times 13 equals 52 square centimeters. Now we're going to do the same thing that we just did for triangle VPR, which is this one right here. Or if you're looking at our net, now is this triangle. I know the base is 10, but I can't find the area of this triangle until I figure out what the height is. So we go back to the diagonal that we've created, and I know MQ is the same as MT. So MQ is half the distance of QR, which means this distance is 4, which means this distance over here from the center to the side length is also 4. So now I'm dealing with a different triangle in red. I have, if I want to find the distance of V to T, then so I have 4 squared, I guess it doesn't matter which way, 4 squared plus 12 squared is going to equal my new height of VT squared. So that means I have 16 plus 144, and that's going to equal 160. So my answer in this case is going to be the square root of 160. That's not a very pretty number, but that is going to happen often. So my height for this triangle, if you look back to the net, is the square root of 160. All right, now I need to find the area of that triangle. So the area of triangle VPQ is 1/2 base times height, 1/2, and the base, now we're looking at a base of 10 and a height of the square root of 160. So the area of VPQ is going to be 5 times the square root of 160 square centimeters. Now again, when I'm dealing with square roots, really, really important, save it for the end. If it does not equal a whole number, leave it as an irrational number, as the square root of 160. All right, so now let's go back to the net. Here's where we put everything together. I know the area of the rectangular base is 10 by 8. Let's see. Let's go with black. And I know that I can add to that 2 of the areas of VQR, because these are the triangles opposite each other. So that's going to be 2 times 52, and then I'm going to add the area of VPQ and its opposite, so these two. So I'm going to have 2 times, what did we have? 5 times the square root of 160, and that's going to get my answer of 310 square centimeters. That is my answer. That's the surface area of the pyramid. Let's break it down again, just in case you're not sure where that came from. Looking at the net, which I'm circling over here in black, I have the rectangle, That's my first. Then I have 2 triangles with base 8 and a height of 13. And then I have 2 triangles, which actually aren't, they can be pointed that way, with a base of 10 and a height of the square root of 160. So if you remember the surface area, you're just adding up the base area and the area of all the lateral faces. And you have your answer of 310 square centimeters. It seems like a lot of work. It seems kind of daunting. But if you just take it a step at a time, draw a net, know that you're dealing with a lot of triangles and a base, you will be okay. It can be overwhelming, but just draw a net, look at what you need to do step by step, you'll be fine. Next up, we're going to be talking about the volume of a pyramid. Now, the volume of a pyramid, as complicated as the surface area was, the volume of the pyramid is actually quite simple. And what I'm going to do in class is go ahead and give a demonstration that will help show you how the volume of a pyramid relates to the volume of a prism with the same base and height. Ooh, it's a cliffhanger. See you later.